Okay. Let's go to the
Okay, I just got mine up.
Me too.
Sorry, my long. Okay, I am good to go.
Cool. I'll start off on number 3. It says use normal probability applet to find the confined area under the standard normal curve that is to the right of z-score 1.358 and to the left of z-score negative 1.358. Round your answer to 3 decimal places. 1.358. Okay, I got 0.1745.
That's what I got.
Okay.
Yep.
0.175.
Oh.
Yeah, I gotcha. Rounded to 3 decimal places, yes.
Yeah.
Yeah, correct.
Which of the following will have a smaller standard deviation if observations are randomly drawn from a population?
So would we be able to calculate that where we don't have any numbers? I mean, I guess we know how many.
Yeah, what they're trying to get you is, so the first one, the distribution of individual observations, that's the population distribution.
Okay.
So its standard deviation is just that sigma, that little O with the little hook. That's called sigma. And then the second one is saying the distribution of sample means X bar. So now it's talking about the sampling distribution with a sample size of 9. So instead of basically graphing every individual point, you are taking groups of 9, finding the average, and only graphing that average. So, and if you remember from lesson 6, the sampling distribution standard deviation is that sigma divided by the square root of n.
Mm-hmm.
So does that make sense?
Yep.
So what you're saying, so you've got some value, and if we want a number, we can put it in there. So let's say for the first one, the individual, just pick one. So let's say sigma equals 9. Okay, so on the first one, so we're saying, hey, the population standard deviation is 9. So then that means that the second one, that sampling distribution wouldn't just, the standard deviation wouldn't be 9, it'd be 9 divided by the square root of 9. Does that make sense?
Yeah.
Oh, okay. Yeah.
And so what's happening is when you divide by a number that is larger than 1, it's going to shrink that value.
Okay.
So what they're trying to get you to understand is that the sampling mean distribution will always have a smaller standard deviation than the population distribution by that division of square root of n.
Okay.
Does that make sense?
Yeah.
So you're trying to relate those things. One's just plain old sigma, and the other one has a standard deviation of sigma divided by the square root of n. And because n's got to be a number larger than 1, that value will always be smaller.
Okay.
I got you.
Mm-hmm.
Okay, that helps. So thank you, because I was a little confused there.
Yeah.
Okay.
I mean, yeah. Again, because it's kind of new, so that they're just trying to get you to say, almost it would be like, no matter what, the sampling distribution will always have a smaller standard deviation. It will always be closer squished together than the population distribution.
Okay.
Okay.
That's really helpful.
Yeah.
Okay, so question 5. Which of the following which of the following results implies that in the spread, so x bar, that's just like a filler, right? I mean, it's the
That's a mean. That's a
Okay.
sample mean.
Okay.
So like if you just went and grabbed 9 observations and you looked at those 9 values and you found the average of those 9 values, that's a sample mean.
Okay.
Because it's just a very simple sample.
Okay. So it decreases as the sample size increases.
So this is again about standard deviation, about things getting closer and closer and closer together. And what law did they give you from lesson 6? And they like this law too. This is another good one for your notes for the central limit theorem, and this one is a good one for.
Oh, the law of large numbers, is that?
Yeah. Yeah, no, it's like central limit theorem. So here's how I always think about it. The central limit theorem is about shape. So it's saying, hey, if you get a sample size large enough, we can guarantee that the shape is normal. The law of large numbers is about how wide or skinny that shape ends up being. And the way they explain it is X bar, that sample mean, gets closer and closer to the true mean. And if it's getting closer and closer, that means all the data is getting squished together, which means the standard deviation is getting smaller. So I always think a central limit theorem is about what's the shape going to be. Numbers is about how wide or skinny it's going to be.
Okay.
Okay.
Does that make sense?
Yeah.
So the law of large numbers is about the overall spread of the data.
Okay.
Kind of, sort of?
Yep.
No, that makes sense. It does.
Okay.
All right. Number 6. Scores on the quantitative portion of GRE are approximately normally distributed with a mean of 150.8 and a standard deviation of 8.8. Diane earned a score of 160 on the quantitative portion of the GRE. What is the score corresponding to Diane's score?
I had to go get my calculator because I'm so old school. I actually use a calculator.
Are you guys just going to use the formula Z score equals X bar minus standard deviation over, I always forget what that one is.
It's
the circle.
That's your standard deviations. So remember, to find the Z-score, you first need to find the distance the point is from the mean. So that's the subtraction. Once you found the distance, now you divide by the value of the standard deviation, and that's going to standardize that score in terms of, so whatever your Z-score is, the unit of measure is standard deviations. So it'll tell you this data point lives this far away from the mean in units of measure standard deviations.
And this one, you don't have to divide by the square root of n, right?
No, because n is 1, right? We're looking at individual scores. We're just looking at Diane, the n.
Yep, okay.
So in essence, you could say, yeah, divide by square root of n, square root of 1. But yeah, you're looking at, and that's such a great question because that's one of the first things I do when we start getting, like, sometimes they're asking about an individual, sometimes they're asking about the average of so many. I'll say to myself, am I dealing with just a single data point, or am I dealing with a group of data points? And that'll tell me if I'm dealing with a single data point, I'm dealing with the population distribution. And if I'm dealing with a group of points, I'm dealing with the sampling distribution.
Okay.
So what'd you get for your Z-score on 6?
Well, for mine, I got 1.045.
Perfect. So yeah, so what it's telling you is that score of 160 lives to the right, because that z-score is positive, 1.045 standard deviations.
That's what I just got right here. 1.0454.
Yep.
However many.
Yep.
Does that make sense, what it's communicating to you?
Yeah.
Okay. Okay.
Number 7. What is the probability that a randomly selected student will score above 160 on the quantitative portion of the GRE?
Okay, so now that we've got that z-score, we can use that normal probability applet, and it'll do all the ugly calculus for us to figure out that area under the curve above 160, which has the standard score of 1.045. The middleman that allows us to use an applet and not have to go use this it's a really ugly calculus. Well, it's a really ugly formula, and then you have to take the integral if you were having to do it by hand. So we're really happy for z-scores. Z-scores make us not have to do calculus.
Yes.
So as annoying as that z-score formula is, if you saw the formula for the bell curve and then the integration, you'd be like, oh, give me the z-score all day long.
Okay, well, for 7, I got 0.148.
Yeah, that's what I got. And you just did the right side, right?
Mm-hmm.
Yeah.
Perfect. Yeah. So there's basically a 14.8% chance that any selected person would get a score above 160.
Okay.
Does that make sense?
Yeah.
Yep.
Okay.
That's not very high chances.
No, and not. So yeah, exactly. So 160 is a great score.
So a random sample of 5 students was selected to take the GRE. Their scores are 160, 175, 163, 149, 153. What is the z-score corresponding to the sample mean of these students' scores? So I need to find the mean.
Okay, so here's where you're shifting gears, and now we're not talking about the population distribution anymore. We're talking about the sampling distribution, because we're not looking at an individual. We have randomly selected 5 students, and we are going to look at their average score.
Okay.
So the first thing you've got to do is you've got to figure out what is that average, that X bar, as we call it.
Okay.
And then the next thing you need to do is you need to figure out what is the sample, or what is the mean of the sampling distribution, and what's the standard deviation of the sampling distribution. Then you go to the z-score. So I almost wish they'd broken this into a couple questions. Am I making sense?
Yeah.
Okay.
I got a mean of 160 and a standard deviation of 10.049.
Okay, so you don't need the standard deviation of those 5 data points. You need it of the sampling distribution. So that's that sigma divided by the square root of n. So in our case, that's going to be 8.8 divided by square root of 5. Does that make sense?
Yeah.
Wait, so where did the 8.8 come in? That's what I'm confused on. Is this?
I think it's given to us up above.
It is. It's given you in the information.
Oh, okay. That's what I was like, where is that at?
So the sampling distribution. So because we're now looking at averages of 5 people, you've got to throw out that picture of the population distribution, and you need to bring in the bell curve of the sampling distribution. And the bell curve of that sampling distribution is still going to have that same mean, 150.8, but its standard deviation is going to shrink. It's not going to be 8.8. It's going to be 8.8 divided by the square root of 5.
Okay.
And that's the picture we're going to deal with now. Does that make sense?
Yeah.
Mm-hmm.
So that's one of those things. It's like, okay, that's how your brain has to work. Am I dealing with the sampling distribution? Bring in that picture, set up my mean and my standard deviation values.
That's fine. That's fine.
So I'm just going to draw it. Not that you can't all see it, but because I'm visual, I want to make sure I am explaining, and I'm not super verbal. Like I talk obviously, but I don't know that I am great at communicating when I'm verbal, because I'm like, that's just not my strength. I'm like, am I making any sense? And then people will be like, yeah, and I'm like, no, I'm not even making sense to myself. But so basically you're always, let me share this. Let's see if it'll share. Draw, and that's another thing you draw. So you basically have either a population distribution, in which case, whoops, if you're dealing with an individual, nice bell curve, huh? You have a mean of mu, standard deviation of sigma, sampling distribution, SAMP, and you've got, we'll deal with the bell curve, and it's got a mean of mu, deviation at sigma divided by square root of n. You're either dealing with this scenario or you're dealing with this scenario. And since they told us that we're getting an x bar, they gave us 5, and they told us to find the x bar. When we're told we're having n is equal to 5, this picture. We're not, you got to ignore this picture right now. Okay, the means are the same. So 150 point, was it 8? I can't remember.
8.8.
Go back and look. Oh, it's 150.8. Okay. Yeah. And so now this standard deviation is 8.8 divided by square root of 5.
Okay.
Let me move that for a sec. 8.8 divided by square root of 5. And then you said you found an x bar value to be 160, correct?
Yeah.
Yeah.
Yes.
Figure out rate of 160 or equal to what in this picture. So now all of a sudden we're doing 160 minus 150.8 divided by not simply 8.8, but 8.8 of 5. So, and be careful you do your order of operations correctly.
Mm-hmm.
This needs to be in parentheses, and this needs to be in parentheses. Or she'll get the wrong answer. Does that make sense?
Yeah.
Yeah.
It's a lot better when it's like drawn out like that. Otherwise, it's like scrambled in my head.
Yeah, and see over here we had, this one was that previous question was just the 160, and it had a z-score equal to 5 is what we figured. And then we found this area.
Mm-hmm.
But this z-score will be different because it should be a bigger z-score because this we're dividing by a smaller number.
So the z-score I got was negative 2.33 or negative 2.3.
Because it's 160 minus 150.8.
Mm-hmm.
So we got 2.337 or 338 rounding.
Yeah, that's 2.3. Yeah, that's what I got. 2.8. Okay, so does that even give us to the... Okay, now we need to go into your z-score. I mean your z-score, your normal probability applet. You're out. Yeah, right? And it's not going to be equivalent to this area over here. Because this sampling distribution is skinnier. By the law of large numbers, this is skinnier distribution. So there should be less area now over here. Of 160. This is an individual score. This is an average score of 160.
So is that, let's see. So, because for question 8, it just wanted the z-score, right? So is it question 9 that wants the probability?
Right,
okay.
Yes. I looked at the wrong thing.
No, you're good. I was just like, wait, did I miss something here?
No, I was not looking at the right number.
I got an area of 0.0097.
Yeah.
Okay, so that would round to 0.097, so 0.01, yeah.
Okay.
If you rounded it to 3, this area would be 0, right?
Yeah.
Okay, so let me just kind of explain. So now all of a sudden, like before, you had a 15.8% chance that you would find a single person 60. Basically, only a 1% chance that you could go out and grab 5 people and their average score would be above 160. So it's a lot harder to go out and randomly select 5 people and get an average score that's above 160 than to randomly go out and just get a single person whose score was above 160. That makes sense?
Mm-hmm.
Yeah.
And think about that in ACT world. Like one person who got a 34, but to randomly know 5 people whose average score was 34 is pretty small chances. Does that make sense?
Yeah.
Yep. Okay, so question 10. Suppose the mean GPA of BYU Idaho students is 3.5 and the standard deviation is 0.7. It is well known that the distribution is left skewed. A random sample of 81 students will be drawn. What is the shape of the sampling distribution of the random variable x bar, which represents the sample mean of the 81 students who are selected? Left skewed, is that right?
What did you say? Sorry, you cut out.
I said left skewed because it said that the distribution is left skewed.
Mm-hmm. There's a sample of 81.
Oh, that's true. So
I think it's you.
So this is where the central limit theorem. That is sample size
large.
Above 30.
Yep.
They're large. So what can we say about the sampling distribution? What's the shape?
Approximately normal.
Yeah.
Oh, you're right.
So the central limit theorem is going to kick in and tell us, hey, even though the is left skewed, distribution should be approximately normal because we have such a large size.
Yep.
Right. Yeah.
Okay.
So
perfect.
Number 11.
This starts to sink in, I promise.
Okay.
It's a little overwhelming at first, but it starts to sink in. So much, it sinks in.
Question 11. What is the mean of the distribution of the sample mean sampling distribution for all possible samples of size 81 that could be drawn from the parent population?
So what do you know about the mean of the relationship between the mean of the population distribution and the mean of the sampling distribution? Right here. So basically what they're saying is, what can you tell me about this value and this value? What do we know? The population distribution, the sampling means are what?
That
they're equal.
Yeah. This one's 150.8. This one's 150.8. They should be centered around the exact same value.
Okay.
They're always centered. If it's the true value, it's always going to be centered around it. Always going to be centered.
Okay. Well, this one,
whether you're taking an average.
Yeah, that's
yes. In this case, it's 3.5. So whatever the population mean is, that is the same mean of the sampling distribution. I mean, truth is truth. If it's true, it's It lives in the same place. It's truth is truth.
Okay.
But it's different with standard deviation, I'm guessing.
Yes, because remember the standard deviation, because now you're taking averages of groups. That law of large numbers is telling me that this should get skinnier. So the standard deviation, because now I'm taking averages, I should get a skinnier version of the population distribution.
Yeah.
What is the standard deviation of the distribution of the sample means for all possible samples of size 81 that could be drawn from the parent population?
So what's the formula for this? What's the formula we use to figure out without actually having to go out and there's the formula? We were like, hey, distribution, standard deviation, then I can use that information to figure out the sampling distribution and standard deviation. Right?
This is the standard deviation divided by the n squared.
Yes, exactly.
Okay.
The standard deviation for the population was 0.7. Sample size is 81. So the sampling distribution standard deviation is going to be
0.07777.
Yeah, 0.078 is what it'll be.
Okay, everybody good with that? Those are like major big ticket items to understand that relationship between distribution and the sampling distribution. Mean of the mean is the mean. That's how I always say it. The mean is the mean is the mean. What differs is that sampling distribution is going to get skinnier by that division of the square root of n.
Okay.
Yeah, that makes sense. Okay.
Okay.
Sorry, I don't know if it's my turn or not, but I'll read. Question 13.
Okay.
What is the probability that the mean GPA for 81 randomly selected BYU Idaho students will be less than 3.3?
Okay, so consider drawing this out. I mean, if you're a visual learner, which, you know, draw the information, consider drawing the information out, and that'll help. If you're a verbal learner, then probably not so. Visual, then you're like, okay, so I know I'm dealing with the sampling distribution because I'm dealing with the average of 81. So I'm like the mean, and the mean's the mean. So this is 3.5.
Yeah.
Deviation is equal to 0.7 divided by the square root of 81. And then they asked me to figure out what's the probability that I'd get an average 3, or was it less?
Yeah, less.
Less than 3.3.
Okay. So this area. So there's how I would draw it out. So that's I take all the information and I just get it drawn out in my brain. Because words are not my So to find that area, I got to go through the middleman Z and that Z score. So let's make sure we're all on the same page on what that value is.
So I have a score of 2.571.
Yep.
And then I got the area is 0.005.
Perfection. Good job, guys.
Yep.
If you can get that, at the end of this lesson, if you can kind of feel that, that's awesome. You can get that relationship and kind of flow through that.
Question 14. What is the probability that the mean GPA for 81 randomly selected BYU students will be greater than 3.3?
Now it wants all this area.
So that would just be 0.994 or 995, I guess.
Yeah, you can use the complement rule because you know the bottom part was 0.0 because you knew that this was got a p-value probability 0.005. This whole thing has to equal 1. So this has to have a p-value of 0.995.
Okay.
You know, or you can go into your probability applet and just unshade the left and shade the two areas to the right, whatever works for you.
Okay.
95.
How's it going? Is it good? Are you good, or am I telling you too much?
No, this
Sometimes
is actually really helpful.
Yeah.
On this.
Yeah.
All right. Number 15. The United States Coast Guard assumes the mean weight of passengers in commercial boats is 185 pounds. The previous value was lower, but was raised after a tragic boating accident. The standard deviation of passenger weight is 26.7 pounds. The weight of a random sample of 48 commercial boat passengers were reported. The sample mean was determined to be 177.6 pounds. Find the probability that a random sample of passengers will have a weight that is as extreme or more extreme. Oh, then
I'll explain that to you. It means basically the extreme or more extreme means you find, so draw it out, and then you have to shade both the left tail and the corresponding right far tail. So first, let's just draw it out. So here's what you know, again, this is how my brain is. I go through and I go, okay, so what's the standard deviation? And I guess up here I should have the sample size. So I was told it was 48, correct?
Yes.
I mean, I just have to organize the information. And then the mean was 176, was it?
Yeah.
And the standard deviation, the standard 20, so this is going to be 26.7 divided by square root of 48, right?
Yeah.
Yeah.
Now that I have that, then I draw myself a picture. And you so don't have to do it this way, but this is how my brain works, so. So now that I have that, then it asks, so the sample mean was determined. Oh no, the sample mean was determined at 177.6. What was the 185?
185 is the mean weight of passengers.
Okay, so this is 185. X bar is 177.6. That's this should be 185. Sorry about that. So 185. So then it's saying, okay, so somewhere down here, there's an X bar 1.6. And then here, extreme, and then come up here the matching extreme. That's what that means. Okay. So once we figure out the Z-score in the normal probability applet, we will shade the far left and the far right.
Yeah.
What we call a two-tailed test. Does that make sense? My picture makes sense to you?
Yeah.
Okay, so once so again, I take all the words and I just kind of get a picture. I kind of get the pertinent information written down, and then I kind of draw out what it's telling me. Now just process through. So now I need to figure out what is the area. So I got to go through the Z-score, and then I just go to the normal probability applet.
Did you guys get a Z-score of 1.920?
Yep.
Okay.
Okay, you guys are ahead of me, so you're doing awesome. And you agree, so perfection.
And then the area, did you get 0.0549?
Yeah. And I just did the
0.0.
extreme. Yeah. 0.0549. Yep.
0.0549.
Yeah.
So 0.05. So 0.055.
Yeah.
Yep.
Okay. Yeah. Awesome. Okay. Yay, you guys! That was awesome. That's hard. That's hard. You did awesome.
Woo.
Got it.
Awesome. Are you guys?
Okay.
All right. Do you submit?
Yes.
Mine's thinking about it.
Nice.
There we go. 100%.
Woo.
Awesome.
Okay. All right. So more important than the 100% on the quiz is are you feeling like the information kind of gelling a little bit?
I'm much more
Yes.
comfortable with it now during the reading and trying to figure out some of the things it just kind of went over my head. So it's definitely making more sense.
Yeah, and check the announcement sometimes, because I'll add like, here, watch this video or something where I feel like, again, I'm so much more visual. I'm like, all right, think about this, or here's the key point to really keep track of. Consider, I know you guys have busy lives, but consider doing the homework quiz like in the next day or so while it's still kind of fresh, to get yourself that practice again.
Yes.
Solidify. Then if you let it go cold, try and remember it. It's harder to solidify it that way. So while it's warm, go in and see if you can get through that homework quiz, and that really helps you.
Okay.
Feel good about the concept. Like, welcome to the next 3 units, basically. I mean, that's how much we do with sampling distribution.
Okay.
I'm glad you were here for this lesson, because
This was helpful.
Yeah, for sure.
Okay, yeah, well, as long as I didn't overhelp, so you're like, I don't know, I can't remember what she said. I'm like, oh, then I overshared for sure.
No, that was very helpful.
Yeah, thank you.
Oh, yeah. All right. Okay, well, let me know if you get to the homework quiz and you're like, okay, I'm not still there. Just shoot me a text or an email so I can get really clear with this.
Okay.
Thank you, Sister Lemon.
Yeah, thank you.
All right, you guys, have a good day.
See ya.
All right, bye.